Welcome back to the Deep Dive. We are looking at a topic today that it really feels like it has fundamentally shifted the ground beneath our feet.
It really has.
And honestly, the stats completely back that feeling up. I was looking at AI adoption rates recently, and it's just staggering.
It's moving so fast.
Something like, what, 44% of IT professionals are already embedding AI into their programming workflows? And another third are actively experimenting.
Yeah, so we're talking about a technology that has achieved, near universal penetration in the tech sector in the blink of an eye.
In the blink of an eye.
But what I find even more compelling is how that adoption is bleeding out of the IT department and into the kitchen, literally.
Right, you're talking about the Tim story.
Exactly. So on one hand, you have IT directors integrating these huge, large language models, right?
Mm-hmm.
And then you have this anecdote from the research, a mother who uses a chatbot she explicitly named Tim to generate enchilada recipes.
And Tim is apparently pretty good at it.
Apparently, Tim knows his way around a spice rack.
I love that juxtaposition because it just perfectly frames the moment we're in. It feels like AI just arrived yesterday with ChatGPT.
Yeah, everyone thinks it's brand new.
But the reality is so much more complex. That enchilada recipe and the automated code, they're the endpoints of a very, very long and pretty chaotic timeline.
That is the big misconception. We think of 2022 as the birth of AI, but it was really just the debut party. The actual gestation period goes back nearly a century.
A century.
If you want to understand why your phone can write a sonnet today, you have to go back to World War II code breakers, you have to look at the physics of silicon, and you have to understand this decades-long war between different ideas of what thinking actually is.
And that is our mission today. We're going to trace this history from, vacuum tubes in the 1940s all the way to the corporate arms race between Google and OpenAI.
It's a wild story.
But I want to start with the fundamental question. Why now? We've had computers for a long time. Why did the big bang of intelligence happen in the last decade and not, say, in 1980?
Okay, so to answer that, you have to look at the three ingredients of AI. You need data, you need algorithms, and you need compute power.
Yeah.
For 50 years, we usually had one, maybe two of those things, but never all three at the same time. The story of AI is really the story of the hardware finally catching up to the math.
So let's go back to the bedrock, the math. We're starting in 1939. Europe is dissolving into war, and the Nazis are using the Enigma machine.
Right, for all their communications. And the Enigma was, for all intents and purposes, considered unbreakable.
Why? What made it so tough?
The variables changed every single day. A human being just couldn't calculate the permutations fast enough. The Allies needed a counterintelligence solution that didn't sleep and didn't make math errors.
And this is where Alan Turing enters the picture. He's usually just framed as the codebreaker guy, but his ambition was so much wider than that, wasn't it?
Much, much wider. Turing didn't just want a calculator. He wanted to build a universal machine. He basically laid out the theoretical bedrock for the entire modern digital world.
He was the first one to really pose that sort of uncomfortable question. Can machines think?
He was. I think he had that famous quote, something like, "I don't think my daughter will ever marry a computer, but I think computers will be doing the things that men do."
Which was just a radical concept back then. Computer was a job title for a person, usually a woman, doing arithmetic.
Exactly. But Turing ran into a wall, a physical wall. By 1946, they had the theory, but the hardware was, let's just say it was archaic. They were using vacuum tubes to process information.
And for anyone who hasn't seen a vacuum tube, we're talking about glass bulbs. They're basically light bulbs that acted as on-off switches.
And they were terrible. Just awful. They were hot, they were fragile, they were huge. The early military computers took up entire warehouses.
You'd need a dedicated power plant just to run one.
And you had technicians literally running around with shopping carts full of replacement tubes because they burned out so fast. You just cannot build a brain if its neurons keep exploding.
So the theory was just stranded, waiting for better physics.
Until 1947. And this is where the breakthrough happens with the invention of the transistor.
This is arguably the most important invention of the 20th century.
You could absolutely make that case. Bill Shockley and his team at Bell Labs, they figured out how to use semiconductors, specifically germanium at the time, to do what a vacuum tube did, but without the heat or the size.
Can you just explain the semiconductor part for a second?
Yeah.
Why is that specific material the key?
It's right there in the name. It's not fully a conductor like a copper wire, which lets electricity flow freely.
Okay.
And it's not an insulator like rubber, which stops it. It can switch between those two states. It's a gate. It can say yes, which is a 1, or no, which is a 0.
And if you can control that switch on a microscopic scale, you can build logic.
You can build a computer.
Yeah.
So Shockley wins the Nobel Prize for this, but he decides he wants to cash in. He moves out to Palo Alto, which wasn't Silicon Valley yet. It was just fruit orchards. And he starts Shockley Semiconductor.
And he recruits the absolute brightest minds in the country. He gets 12 geniuses, including guys like Gordon Moore and Robert Noyce.
But there was a huge problem. Shockley was a brilliant physicist, but he was a disastrous manager.
The big mad hater management style.
Laughs. That's one way to put it. He was paranoid, controlling, abusive. It got so bad that 8 of his top scientists became known as a traitorous 8. They just walked out.
And they went down the street and founded Fairchild Semiconductor.
And this right here, this is the true birth of Silicon Valley. It wasn't just about the tech. It was about this new culture of, equity and spinning off new ideas.
And Fairchild makes a crucial pivot. They stop using germanium and they switch to silicon.
Yeah, silicon was harder to work with, but it was everywhere. I mean, it's basically sand, and it handled heat much, much better. Plus, it allowed for the creation of this natural insulating layer. That was the game changer.
And suddenly they could sell these transistors to the military for the B-70 bomber navigation systems.
At a massive markup.
But they still had a scalability problem, right? You can make one silicon transistor, but for a computer, you need thousands of them. And someone had to hand solder all those things together.
Yes, the tyranny of numbers. The more complex the computer, the more connections you need. And every single connection is a point of failure. If you've got 10,000 wires, one of them is going to break.
This is what leads to the integrated circuit.
Exactly. Robert Noyce, one of those traitors, he has an epiphany. He thinks, instead of making separate components and wiring them all together, why not manufacture all of them? The resistors, capacitors, the transistors, directly onto the same slice of silicon.
No wires.
No wires. A solid block.
It sounds so obvious now, but that was just science fiction then. It's like print me an entire city block at once instead of building house by house.
That's a great analogy. And that innovation that sparked the exodus from Fairchild, the Fairchildren, as they were called, left to start Intel, AMD, LSI, Logic.
Wow.
Today, something like 92% of the world's computing power traces its lineage right back to that one office at Fairchild.
So we have the chip, but we still need it to get personal. We need the microprocessor.
That happens at Intel in 1971. They were trying to build a set of chips for a Japanese calculator company called Busicom.
Okay.
The design was just too complex, too many different chips for different functions. And an engineer named Ted Hoff just said, wait, let's make one chip that is programmable, a general-purpose brain.
That's the microprocessor.
That's it. That's what allowed computers to shrink from the size of a warehouse to something that could fit on your desktop.
Okay, so by the 70s and 80s, the body of the computer is ready. We've got the silicon, the chips, the PCs are coming.
The hardware's there.
But the AI was lagging way, way behind.
It was. While the hardware guys were winning, the software guys were kind of struggling. Back in the 50s, Marvin Minsky had built the first neural network using hardware, but it was really primitive. Then in the 60s, you had ELIZA.
The first chatbot.
The first chatbot, yeah.
And ELIZA is fascinating because it tricked people. It wasn't actually smart, but it felt smart.
It was all pattern matching. So if you typed, I am sad, it would look for the keyword sad and just swap the syntax to ask, why are you sad?
It didn't understand sadness at all.
Not even a little. It was a parlor trick. But what it showed was that humans are just desperate to project intelligence onto machines.
But because these tricks didn't lead to actual, real intelligence, we hit the AI winter.
Right. Funding dried up completely. Everyone just thought AI was a dead end.
Until the mid-'80s.
Until the mid-'80s. A researcher named Geoffrey Hinton, and you should remember that name, he kept the flame alive. He was working on something called backpropagation.
Okay, let's unpack backpropagation, because this seems to be the fundamental mechanic of how all modern AI learns.
It really is. Think of it like a teacher grading a test. The AI makes a guess.
Okay.
The teacher algorithm looks at the guess, it sees how far off it was from the right answer, and then it sends a signal backwards through the neural network saying, okay, adjust your settings by 2% in this direction.
So it allows the network to actually learn from its mistakes.
Over and over and over again.
So instead of programming the computer with rules like, if the object has whiskers, it's a cat.
Right.
You just show it a million pictures of cats and let it figure out the rules for itself by by failing repeatedly.
Precisely. But there was a catch, a big one. Neural networks require an insane amount of math, matrix multiplication specifically. And in the 80s and 90s, standard computer chips, CPUs, were just way too slow to do it effectively.
Even Deep Blue, the IBM computer that beat Kasparov at chess in 1997, that wasn't a neural net, right?
No, not at all. That was what we call good old-fashioned AI. It was just brute force. It didn't learn. It just calculated millions of moves per second to find the best path. It was a triumph of power, not intelligence.
Which brings us to the Big Bang, 2012. The moment where the hardware finally met the software.
This is the convergence. This is the key moment. You had big data thanks to the internet.
Right.
You had better algorithms thanks to Hinton and his students. But the missing piece was the engine, the compute power.
And the solution came from a totally surprising place. Video games.
It's one of the great accidents of history. NVIDIA had been making these things called GPUs, graphics processing units for gamers.
Right.
Now, a CPU is like Ferrari. It's really, really fast at doing one thing at a time. A GPU is more like a fleet of school buses. It moves a ton of data more slowly, but it does it all at once.
Parallel processing.
Exactly. And it turns out rendering a 3D video game requires the exact same type of math as running a neural network. You're adjusting millions of pixels all at the same time.
And Hinton's students figured this out.
His students, Ilya Sutskever and Alex Krzyzewski, they realized this. They plugged their neural network, which they called AlexNet, into 2 NVIDIA GPUs.
And they entered the ImageNet competition.
And they just obliterated the field. I mean, it wasn't even close. They proved that with GPUs, neural networks actually worked.
This was the moment.
This was the moment Jensen Huang, the CEO of NVIDIA, bet the entire company. He realized, we aren't a gaming company anymore. We are the engine of AI.
And that one decision made NVIDIA a multi-trillion-dollar company.
Yeah.
But it also kicked off the corporate war.
It did.
Because suddenly everyone realized AI wasn't some sci-fi dream anymore. It was the future of, well, everything.
And Google moved first. They bought DeepMind. They hired Hinton. They basically tried to monopolize the entire global supply of AI talent.
Which did not sit well with the rest of Silicon Valley.
No. Elon Musk, Peter Thiel, Sam Altman, they all looked at Google and got genuinely scared. They thought if one company controls superintelligence, that's basically a dystopian nightmare.
So they founded OpenAI as a countermeasure.
A nonprofit open source lab to democratize AI.
And the hiring war got personal. Musk poached Ilya Sutskever, the guy from the AlexNet breakthrough, directly from Google.
Which completely ended Musk's friendship with Larry Page. I mean, it was a serious betrayal in the Valley, but OpenAI had a problem.
They were a nonprofit.
They didn't have a revenue stream. And training these massive models on NVIDIA chips cost hundreds of millions of dollars.
Before we get to that pivot, we have to talk about the technology that made those costs skyrocket. The Transformer. Google invented this in 2017, right?
Yes. The paper was called Attention is All You Need. It was a breakthrough. Before this, AI read text sequentially, left to right.
And it would forget the beginning of the sentence by the time it got to the end.
It would. The Transformer allowed the AI to look at the entire sentence at once and pay attention to how all the words relate to each other.
So it understands that bank means something different in Riverbank versus bank account based on the context.
Exactly. It allowed for a depth of understanding we had never seen before. But here's the great irony. Google invented the Transformer, but they were too cautious to actually deploy it.
Why?
They had a search monopoly to protect. If you have a perfect chatbot, you don't need to click on ads.
But OpenAI didn't have that problem.
No, they had nothing to lose. But they desperately needed cash for compute. So they made the very controversial decision to cap their profit and take a $10 billion investment from Microsoft.
This is when Musk walked away.
Yeah, he felt they betrayed the entire mission. He said they turned from an open-source nonprofit into a closed-source subsidiary of Microsoft. But that money bought the GPUs that trained GPT-4.
And when ChatGPT launched in late 2022, it reached 100 million users faster than any app in history.
It signaled the start of the generative era. We aren't just classifying images anymore, we are creating content.
So if you look at the whole timeline, the adoption curves are just compressing like crazy. The car took, 45 years to become mainstream?
The internet took about 10.
And ChatGPT took 2 months.
The friction is just gone. You don't need to buy a new device. It's on the phone you already own. You don't need to learn to code. You just speak English to it. The barrier to entry is basically zero.
But there's maybe a darker side to this, or at least a more complicated one. The whole chip war idea. We mentioned NVIDIA is powering 92% of AI. We're in a situation where the entire infrastructure of the future is incredibly concentrated.
That is the geopolitical reality we have to grapple with now. If compute is the new oil, then Taiwan, where TSMC actually manufactures these NVIDIA chips, is the new Middle East.
Wow.
We are seeing nations start to hoard GPUs the way they used to hoard gold reserves.
It just completely changes the map. It's not just about who has the smartest coders anymore. It's about who has the silicon.
Right. You can have the best algorithms in the world, like Google did with the Transformer, but if you don't have the compute to run them or the business model to deploy them, you lose.
So we've gone from Alan Turing dreaming of a machine that can think, to Bill Shockley shrinking the switch, to Jensen Huang pivoting an entire company to power the brain of the internet. It's a really wild ride.
It is, and we are just in the earliest innings of the application phase. We're just getting started.
So for the listener who is just, using Tim to make enchiladas, or the coder who's using it to write scripts, what should they take away from all this history?
Don't be passive. I think that's the main thing. This isn't a wave you can just sit back and watch go by. The adoption is happening so fast that the wait-and-see approach is just dangerous. You need to get your hands dirty.
So play with the tech, understand the hallucinations, get a real sense of what it can do, and, maybe more importantly, what it can't do.
Exactly. Whether it's going to a site like skillsbuild.org or just experimenting with different models, the literacy of the future is being written right now as we speak.
And on that note, we're going to wrap up this deep dive. Thanks for listening to The History of the Future.
We'll see you next time.